Thanks, Shivashish, for the introduction. Yes, so my talk will be on the research topic that I did during my PhD, and like I'm continuing in the same area of logic and automata, which I found interesting during that time. So I think the starting would be very basic, and everyone who can relate to this because they will know. So we have two formalisms on the side, this logic, and other is automata, which seems very different, but as we know that they both are connected because they both kind of define languages, so there is a connectivity between them, and as we'll see that this connectivity will come into play in the industry role as well. So here in particular, you will see that the logic and the regular expression are defined inductively, whereas automata, if you remember, they are defined directly in terms of a tuple. So there is no inductive definition in terms of automata. So my topic was about building automata from smaller automatons. And all of you have seen a direct product of automata, which essentially takes any input and kind of parallelly executes that. But the kind of product that we were interested in that kind of lets you get down to very small automata to build any general automata is something called cascade product. And so here also the definition is given in terms of tuples, like given two automata you get another tuple, but there is another way to look at it operationally, where if you have two automatons A and B, then you are putting them in a series kind of thing, and the first automaton acts as a transducer, so it adds some information to whatever string it is reading. In this particular case, think that whatever the string automata is reading, A is reading, it adds the state information to each letter. So after reading the word W1, if it reached state S, then it adds that information S to the next letter A, and then the next automaton works on that decorated word, so it has some extra information to use. And finally, the automatons together in terms of their accepting state makes a decision. So for instance, this two automatons, the first one is accepting any word which ends in B, but if we consider this as a transducer that adds the state information to each word it is processing, then the second automaton, I don't know if you can see it, it accepts the words A1, which essentially means that if the A is the starting letter of the word, or if it has been preceded by a B. Because see, the first automaton is special that letter A always takes you to state 2, whereas letter B always takes you to state 1. So for the second automaton, A1 means that the A was just preceded by B or it was the first letter, whereas B2 means the B was just preceded by an A. Essentially, it just accepts AB star. So there is a result in the 1960s that essentially says that any regular language can be accepted by a cascade of these two kind of automatons. One which is just two-state reset automaton. Reset automaton, the term reset essentially here it defines that every letter kind of takes you to one of the two states, or it can not change state, that is also allowed. Identity is also allowed. And the other kind of automaton is that does a permutation of the states. Any letter does that. So why would this be useful? So this actually gives another proof technique to our toolkit. So for instance, this is a very important theorem in formal methods where two logical formalisms over words. One is linear temporal logic, which talks in terms of time, and the other is the first order logic, which you saw earlier. And these two formalisms turn out to be equally expressive. So one direction of the proof is based on structural induction on a linear temporal logic, which is also defined inductively. And in fact, if you work in logic, you will see that a lot of the proofs are based on structural induction because that's how the syntax is defined. But the other direction, even though FO is defined inductively, the other direction of the proof does not go through as easily. But if you have the Kronrausch theorem, it actually tells you that FO is equivalent to a cascade of just the two-state reset automatons. And defining the language of the two-state automatons and their cascade in LTL is quite easy. And this becomes like a one-page proof, which was originally, I think, a 100-page proof in Camp's thesis. So we worked in this kind of decomposition setting. We wanted to approach this decomposition kind of problem of automaton, but in the concurrent or distributed setting. So initially, so what do I mean by this distributed setting? That in automata, you have a string of letters in the word, and you can think of that as a process or a person who is accomplishing some tasks one after the other sequentially. Whereas if we want to think about some actions that can happen parallelly, or if their order doesn't matter, so then you want to model the languages somewhat differently. And one way to define it that was used in the formal community was that you define over the alphabet, you define some independence relation between some of the letters. So here A, B are two actions that are independent, which means that in a word, if they are happening consecutively, then their order does not matter on the final output. You either accept both of them or you reject both of them. Or you can think in terms of this figure that sigma star, the set of all words, is now divided into some equivalence classes, where each class has the word in each class. You can kind of swap things around and reach the other word. And so now our question was that, so now the language over this sigma star is basically a collection of the equivalence classes. Basically, you either accept a whole class or you don't accept that class. And those are called trace languages. And now the question is, can we recognize any trace language using a cascade of DFA, where each DFA is now not just recognizing any regular language over words, but a trace language? Can we do that? And turns out that in this sequential kind of approach for concurrency, this becomes difficult, because if we think the words AB and BA going through a DFA, the states after reading A and after reading B can be different, and the state information that you add to these words becomes such that now you cannot put them in a equivalence class. The letters itself will become different. So the decorated alphabet that you get, how do we define an independence relation on that? What will be the trace language there? Not clear. Now I'll show another setting where another setup where this thing is studied, and that suddenly this question becomes very naturally solvable there. So now we consider alphabet and we kind of use partial order to study them. So we have this ABC alphabet, and we say that there are processes 1, 2, 3, and the job of executing an action in the alphabet is the job of some of the processes. So you can also think of this process as persons. Like every person has some job. Sometimes you do a job on your own. Some of the jobs you do in a meeting with some other persons. So the location function kind of tells you that B is something, a job that person 2 and person 3 have to do together after they meet. C is something that person 1 and 2 has to do together, whereas A is something that person 1 can do on his own. So now looking at this, you can see that because A and B are being executed by disjoint set of persons, they can happen parallelly. So this location function kind of defines the independence for you, and you have a partial order structure for the word that we had earlier. We now have a partial order instead. And the automaton that, there is an automaton by Zielonka that kind of works directly on this partial order, which becomes instrumental in now defining the cascade product. Here the idea is that each process has a local state. So I didn't want to bring in the tuple notation earlier, but unfortunately for asynchronous automata, I think there is no easy graphical kind of view. So for each process I, there are some local states, and the letters kind of define the transitions for the joint states. So the C meeting that person 1 and person 2 did, they were in state S1 and S2 at the beginning of the meeting, and at the end they decided after the meeting that, okay, now our states are S1 prime and S2 prime. This way the automaton kind of moves forward. And the global state is essentially at any point, it is the combination of the states of all three persons or processes. And you have an initial state, which is the global state. Now, how does this help? Well, in the trace setting, now for any letter, you have the local states of the processes that participate in it. And you can add that information based on the run of the automaton. And suddenly that ordering issue that was there when we were considering serializations of traces, that is not there. And based on this approach, we can actually define a product of asynchronous automaton. And in the same way as it worked for DFA, the runs of the individual automatons combine to give a run of the local cascade product. So now that we are defined the cascade product, we can also define some simple asynchronous automaton. And these are like corresponding versions of the simple automatons that were given by the Kron-Roach theorem. We essentially say that only one process will do work. The other processes have a singleton state, so they don't do any work. And if you look at the global state version of the asynchronous automaton, it is simply the DFA that you got in the Kron-Roach decomposition. And so at this point, we are now finally can actually frame the question, formalize the question of what we wanted to do. And it is that, can any trace language be recognized by a local cascade product of this simple asynchronous automaton? And the solution was not present when I completed my PhD, but after that, Shantanu Kulkarni continued this work. And last year, they have formally proved that this is indeed possible. As an open question, the FO version of this is still open. And so we don't know which of the machines it gives the exact decomposition for the FO definable trace languages. So after, at the end of my PhD, my main idea at that time was to join academia actually, but things always don't go according to what you plan, and I joined industry. So thankfully for me, I joined in an area that still let me be in this topic of logic and automata. And as I said earlier, that connection between automata and logic, that plays a part in verification, which is used in hardware industry. It is quite important. It is part of like the flow of any tape out of any hardware module. In software industry, it is being adopted quite heavily in, I think, Amazon and Microsoft. So the basic idea sounds simple. It's that we want to know whether a system satisfies a particular property. And if the system can be modeled as an FSM, which in the case of hardware, it can be done as a finite state system. And the specification usually we define in terms of logic, or usually in terms of LTL, linear temporal logic. Then the question boils down to the behaviors of them in terms of words, usually over infinite words, but let's not, we can skip that part, I guess. And essentially it's saying whether the system satisfies the property then comes down to this, whether the behavior, any run of the system, whether it exhibits a string, whether it contains a string which does not satisfy the properties. So you need to kind of have the ability to do a complementation and intersection of sets of words. And we know that automaton has the capability of doing that. So automaton, you can think of automaton like a data structure that represents a set of words, possibly infinite set of words, which has the capability of doing intersection of set of words and complementation of set of words. Okay, yeah, sorry. Yeah, and in fact, this earlier problem then actually has an algorithm that gives you it gives you a switch. You can directly write the property, and if you have the model, then it gives you a direct solution whether the property is satisfied or there is a counterexample. Unfortunately, as it turns out, all this theory, when it goes to industry, scalability, as mentioned earlier, becomes a problem. And if you have any 100 Boolean variables, then you get 2 to the power 100 states. Suddenly, state exploration of an automaton or becomes difficult. And 100 is just, a toy example actually. So, for instance, you can try this puzzle, which is let's say you have n light bulbs which you can turn on and off with switches attached to each bulb. But the bulb does not only change the state of switch does not change the state only the bulb above it, but also its neighbors, adjacent neighbors, if they are present. And now the question is, can you reach, let's say from every bulb is turned off, can you reach all bulbs turned on? That is one specific example. And the general case would be like, if you are given any state P and Q, how do you reach to the next? Can you reach the state Q from any state P? And if you increase the number of n, let's say to 1000 or 2000, the current state of the art formal verification tools will not be able to do this. You have to come up with some help. You have to come up with some kind of observations about the system, about the problem, and then help the tool to actually prove it. So it feels more like a mathematical exercise doing this formal verification. And at the same time, hopefully, also I can learn about all the techniques that have gone into this. And one particular method, for instance, which somewhat connects to the earlier talk because it was based on traces and partial orders, is that if we have a lot of interacting processes and their interleavings, and there is some kind of equivalence between the interleavings, then you don't want to try every combination of interleavings. You actually want to try only one. And this is an approach called partial order reduction. There was in fact a poster session, I think, poster based on this. So in general, I would say in academia, for instance, in Intel, what we see is that the research that is being done is directly comes from the problems that are being faced. So for instance, I said that in hardware industry, the modules usually can be modeled as finite state systems, which is true, but there are always parameters like how many cache are there in the system, how many requesters will be there, and stuff like that. And there is essentially no bound on the parameters. So then parametric verification becomes important there. And there were a lot of work done based on that from the group that I was in. Whereas in academia, I think immediate impact is not necessarily always needed. And for instance, my own topic, it was about finding a proof technique. There is, I don't think there is any practical application of that. Whenever I talk to someone about that, they ask, how do I apply it in the industry? I have no idea, actually. So, but I think both are important. And because as you can see that even verification, it started in the 80s. There was, I don't know if there was any industrial motivation at that time. It was only later on that other approaches and other advances like SAT solvers and everything suddenly make things easy for verification also, and things to industry kind of found their use. So I guess there is a lot of chance for collaboration between this, because people in academia, they study topics deeply, and based on their interest, but people, most problems in industry, probably they are not aware of how they can apply those knowledge that they have, whereas people in industry, probably they don't know which things they can apply, because sometimes the connections come from unexpected places. So as a student, I would say that you should try to go for industrial internship and just see what is being done. because even if your problem is theoretical and you don't think that directly it would help in your PhD, I think getting some idea of what is being done in industry and what kind of problems they are interested in can help you. And also, so I think that would also help because in terms of funding, of course, even though there is a lot of freedom in academia, sometimes you end up having issues with funding. So having people interested in whether it is in industry or in academic places, knowing that it is definitely needed for your funding later on. So I don't have any other slides, but I'll just mention a couple of small, I guess, advices. One is simply that write down whatever things you have learned during your meeting or whatever you have found out till now. I think what we always tend to do is that we start writing only when there is a paper deadline, and when we feel that, okay, now I have enough to write a paper. But we don't write the day-to-day stuff that we are doing, and we kind of lose, I think, a proper methodical way of doing research in that way. I think in research, we often face this problem where we are frustrated and not able to solve problems. But what's even more frustrating is when you try something and you realize that, oh, I had tried this earlier and I just had not written it down, I had forgotten it. So now I should write it down. Also, writing things down lets you kind of make things clearer to yourself. You may feel like you have understood something or this problem is done, but writing it down kind of makes it become clear that whether how much has been done, and also sometimes gives you other interesting research ideas. And as Priyanka mentioned, yeah, I would again emphasize that you should have empathy, and more importantly, to yourself, be kind to yourself, because we can be our harshest critics, and that is a problem for all of us. So thank you.
So thank you, Saptarshi, for the very nice and insightful talk. So are there any questions? Okay, so maybe I'll ask a small one, which is that you were talking about the trace language and there were some equivalences. So it's exactly not the kind of equivalence you'd see, for example, in Myhill-Nerode, but it was a finer equivalence, right? It was a two-sided congruence.
What can you repeat the question? Sorry.
No. So you were talking about this trace language and their equivalence classes you were showing.
Yeah.
So those equivalence classes were not the kind of equivalence you would see, for example, in Myhill-Nerode, but which is only a right congruence, but here you showed a two-sided congruence, and hence it's finer.
Yeah, there the equivalence classes is just based on this what letters you can swap, and whether you can reach from one word to another word using this swapping of only adjacent independent words, because their order kind of doesn't matter. So yeah, that is different.
So another thing, I mean, I think this thing came up in one of that panel discussion yesterday. I mean, this industry panel discussion, you were talking about collaboration between academia and industry. So one of the things that the panelists yesterday, they were discussing also about how to sort of have more collaboration between faculty members in academia and in the industry. So faculty members, for example, as you were saying that you were doing algebra and proving some Kamp's theorem and come up with a new proof technique, and whereas industry, the problems are motivated by different kind of sources. I mean, so essentially, how do you think that there can be some way to bridge this connection? I mean, do you have maybe just one sentence?
So one thing I think is that often the faculty are okay if the students bring their own problem for their research, right? So even if they are mostly interested in theoretical topics, maybe they can guide someone who wants to do something in collaboration with industry, or at least they can get some co-guide to help together. And in any way, I think it is fine if some professors are totally invested in that kind of research, but there will be other professors who are more interested in some practical topics, and it's up to the student, like which is interesting to him. If he wants something with practical applications, then he should approach appropriate faculty. and find collaborations.
Okay. So if there are, okay, so there is one question.
I had a question. So you mentioned that formal methods have been used in sci-fi for basically doing verification. So is it only like functional verification, or are they looking at formal methods for security verification as well?
So this term functional verification, I see it used in very different meanings, semantics. So I don't really get the question, I guess. But so what was the last part? Like, what kind of formal verification we are doing, or?
So like functional verification in the sense that, whatever, like for example, an ALU is working correctly or something along those lines. Whereas is like formal verification also being used for ensuring the security of the product?
Okay, so yeah, so formal verification in the way, I guess it is this mathematical approach of directly modeling in terms of automatons or theorem provers and stuff, and that is indeed being used in all the hardware companies, I think, as part of sign off of any product. Yeah, I'm not sure about functional verification. I think that I have seen it being used in different meanings, so I'm not sure about that one.
Okay, so maybe in the interest of time, we can take the remaining questions offline. Sure. And let's thank Saptarshi again for the talk. So our next speaker is Shruti Shekhar, who is currently an assistant professor at IIT Bombay. So prior to joining IIT Bombay, Shruti was a postdoctoral research at University of California, Berkeley. And she did her master's and PhD from Indian Institute of Science, Bangalore. So Shruti's research interests are in the area of cryptography, both theoretical as well as applied cryptography. And she has published in numerous top-tier venues in her area of research, and her work has also been recognized through several awards. So notably, she, for her thesis, she received an honorable mention at the ACM doctoral dissertation in 2022, and also she has been a recipient of TCS fellowship and several other fellowships. So today she is going to talk about robust crypto systems. So over to you, Shruti.